Spectra are useful for very many things in astronomy. In the last video we talked about how you can look at the absorption lines and work out what something is made of. In this video I want to talk about how you can use the Doppler effect to measure the speed of objects. So let's say we have something in space, let's say a star, and let's say it's flying along at some speed. Now let's say it emits a wave of light, and sometime later that wave of light, assuming it's gone in all directions, will spread out in a sphere around it. And then a short time later the star has moved, say to here, and it emits another pulse of light, and that will also spread out. It hasn't got so long so it won't get as far, so it might be centered around here. And some time later our star's got to here and emits yet another pulse of light, which now gets to here, and so on. So what you can see is, even though each pulse of light spreads out in a sphere because it's going at the same speed in all directions, if you look from here, let's say that's your eye, from this direction you'll see the waves are quite close together. But if you look from up here, you'll see the waves are quite far apart. So the wavelength is shorter if something is moving towards you, and the wavelength is longer if something's moving apart. So that is a Doppler effect. How do you measure it? Well, you take a spectrum, and let's say you expect a particular line, an absorption line, to have this wavelength. Let's call it the lambda laboratory. But when you look at the spectrum, you actually see it's over here at a different wavelength, lambda observed. We can measure the shift, which is equal to lambda observed minus lambda laboratory divided by lambda laboratory. This is called the redshift. And you can see it's positive if the line were over here, because in that case lambda observed is bigger than lambda laboratory. That means that the wavelength has become longer than is expected, which means the object is moving away from us. In this particular case, lambda naught is less than lambda laboratory, so this is actually have a negative value, which corresponds to a blue shift. So that's how you measure. It's typically written with the letter Z. Z for any Americans in the audience. But how does that tell you the velocity? Well, to get that, you have to use relativity. It turns out that if an object is travelling at a velocity v, then the redshift is given by the equation the square root of 1 plus v over c, where c is the speed of light, all over 1 minus v over c, all minus 1. So that is the true relativistic equation for redshift. So it all depends on the ratio of the speed of an object divided by the speed of light. So c equals speed of light. That's quite a cumbersome equation to work with. You need it when things are going close to the speed of light, but most things in the universe travel very, very much slower than the speed of light. So in that case, there's an approximate version, which is that the redshift is equal just to the velocity divided by the speed of light. So if something's going at 1% of the speed of light, then the line will shift 1% to the red if it's going away from us, to the blue if it's coming towards us. And that's useful enough for most things we want to do in this course.